This program, EXPANZ, demonstrates the relation between complex exponential sequences and their real and imaginary parts, and it also shows the conditions necessary for these sequences to be periodic. The red ball in the top left panel shows the complex exponential sequence e to the j omega 0 n with discrete time frequency omega 0. It shows it as a vector in the complex plane as a function of time n. We select the value of omega 0 here. The value of n is shown here. We step the value of n forward by pressing on this control here. Each step increments n by 1. The top right panel shows the imaginary part of the complex exponential, which is sine omega 0 n. The bottom left panel shows the real part of the complex exponential, which is a cosine, both plotted against n. The orientation of the plots makes clear that the sine of omega 0 n is the projection of the complex exponential onto the imaginary axis, and the cosine is a projection of the complex exponential onto the real axis. We can now press the play button to increment n continuously. Press the button again to pause. Press play again, and note that each time the vector goes through a rotation of 2 pi, the color changes. Because the frequency is pi over 4, otherwise known as 2 pi over 8, this complex exponential sequence is periodic with a period of n is equal to 8, as shown here. Press stop to stop, and press X to reset everything again to 0. You can use this program to show that discrete time complex exponential and sinusoidal sequences are only periodic if the angular frequency is a rational multiple of pi. For example, let's set the angular frequency to 3 pi over 8 and run the animation. Because 3 pi over 8 is equal to 6 pi over 16, the sequence is periodic. It goes through 3 rotations of 2 pi in 16 points. You can also expand the scale to show only a single cycle and run the animation. Finally, consider an angular frequency which is not a rational multiple of pi. Now when you run the animation, you'll find that this is aperiodic. This program is one of a suite of programs that I have developed to explain DSP concepts to my students during lectures. There are now well over 24 programs covering many aspects of the material in the book, including complex exponentials and sinusoids, convolution, the DTFT, pole zero plots and their relation to frequency and impulse response, A to D and D to A conversion, including upsampling, downsampling, resampling, and aliasing, the design of many types of FIR filters and their application to the filtering of speech and other signals, the design of IIR filters, circular shift and convolution using the DFT, the discrete cosine transform, and the short-time Fourier transform. A selection of these programs is being made available to instructors who are currently adopting the book in their classrooms. For further information, please visit cambridge.org/Holton.